In this lesson, we're going to take a look at another application of vectors, vector addition in particular. We're going to look at velocity this time. Yesterday was force, today is velocity. There's no really new math. We're just going to try and apply the idea of vector addition again and look at resultants. So, take a look at the first example here. A plane travels due north at an airspeed of 900 kilometers an hour. So as soon as I see that there is a direction, I'm going to give myself a compass. And due north means straight north. So on my compass, my plane is trying to fly 900 kilometers an hour due north. It encounters a wind blowing from the west. So west would be from the left, and if it's blowing from that direction, it's actually going towards the east. Okay, and that's going 80 kilometers an hour. What is the resultant velocity of the plane? Well, the resultant, according to vector addition, would be from the tail of the first to the tip of the last. That's our resultant. Now the nice thing about this diagram is it's a right angle triangle. This is just a Pythagoras question. So we can do 900 squared plus 80 squared is r squared. In other words, r is the square root of all that stuff. I got 903.55. That's kilometers an hour. That's how fast the plane is going. So picked up some speed because of the wind. If we're talking about vectors though, don't forget we need to have a magnitude, which we have, and a direction. So we need an angle. Angle will be right here. Okay. That's well, I have, again, right angle triangle, so it's a SOHCAHTOA question. I have the opposite and the adjacent, so I'm going to use my tan ratio. What, 80 over 900, so theta is the inverse of that. And on my calculator, I got 5.08 degrees. Okay, so what is the resultant velocity? The resultant velocity is 903.55 kilometers an hour at, in your direction here, at a bearing of, well, there's a couple ways you could do this. We could say north, and then it's 5.08 towards the east. Or we could literally just say at a bearing of 5.08 because north is 0. Both of those would work. Kind of your choice there. One or the other. Okay, that's it. I'm going to just solve that one. Okay, we can get you guys to try one maybe. So all I really have is examples this lesson. Try pausing the video and try the example yourself so you can figure it out. Play the video and see if you got it right. A plane is headed north 30 east. Oh, need a compass. North 30 east. So there's a 30 in here. At a speed of 800 kilometers an hour. It encounters a wind of 75 kilometers an hour blowing in the direction of, oh, I need another compass because I got another direction here, of southeast. So my wind is going southeast, which means directly between south and east. Probably a little long there. Let's make that wind a little shorter there. Okay, and because it's directly between, we know it's 45 or 45. Okay, there's my wind. Find the resultant velocity of the plane. Okay, so tail of the first, tip of the last. There's r. So, what do we have this time? Oh, I need one more number here. Wind is 75. Oh, I got two sides this time. Doesn't look like it's a right angle triangle. Big hint here is that, well, we have two compasses. And whenever we have two compasses, the big hint there is that you're always, always, always going to have a Z pattern. So if you stop and look here, here's my Z, which makes the angles in between 30 and 30, which combine, this whole angle makes 75 degrees. And the reason we have a Z is compasses have to be parallel, so we can every time when we see two compasses use that idea. So what are we going to use this time? Well, this is actually a cosine law question. Okay, our cosine law is used when we have two sides and the angle between them, which is what we have in this situation. R is the side I want. I have one side of 800. I've got one side of 75. It doesn't matter what order you put those in, and the angle between them is the cos of, well, the angle between is 75. That's that angle right there. And put it all in your calculator, square root it, and you get 783.94 kilometers an hour, hopefully. So this time the wind's actually slowing the plane down. Again, like last time, we need to have a bearing, a direction. It's not right angles, so we can't use SOHCAHTOA, but we now have a pair because R and 75 are across from each other, so we can use the sine law. The sine is 75, goes with that R value we just calculated, 783.94, and what are we trying to find here? Oh, we only need to find this angle, right there. There's our angle, and it's across from sine 70. It's across from the 75, not the sine 75. Okay, bring that 75 up. So kind of like cross multiplying, but not exactly. Now I go to sine theta. We want just theta though, so we're going to take the inverse of this big old mess of stuff. 783.94. And on my calculator, I get, oh, close to the last one. I got 5.3 this time. Okay, so let's answer the question. The resultant velocity is, what was our speed? 783.94. There's our magnitude. At, and last time we could just use the 5. Well, this time we can't quite use that because our bearing is actually from north all the way to that line. So it's 30 plus theta. In other words, it's north 35.3 east. I need to include the 30 plus the theta because that's where my plane actually ends up. Okay, so this one plus the 30. Okay, we'll try another one. A plane is headed north 40 east. They don't always go northeast, just don't fall for that trick. Just made it like that so far. Okay, north 30 east with a speed of 800 kilometers an hour. A west wind, that means a wind from the west, a west wind. So from the west means it's blowing towards the east. Causes it to travel north 45 east. So our plane is actually going here. That's our resultant. The angle is 45 degrees. Now using that, oh, actually that's not a 30, is it? My bad. That's a 40. 40. And the angle inside the diagram is, well, 45 minus 40 makes 5. So this is a 5 inside. Okay. Oh, what else do I got? That's all they gave me. They want me to find the resultant speed. So how big is R? And the speed of the wind. I'm going to call that W. That's all they gave us. So how are we going to solve this problem? Well, there's some things we have to think about. There's actually another compass up here. I didn't draw it in at first, but when it says directly from the west, that's it's a compass direction, which allows me to use my Z pattern again. And here's our Z, goes up and down and up again, which means this is 40. And in compasses, there's a right angle, which makes this entire angle up here in the corner 90 plus 40, or in other words, 130. And if you look at the green angles, we got the 5, the 130. I can figure out the third one because we know triangles have to add to 180. So far I've got 135, which I believe leaves me with 45. So I'll have all the angles in the diagram. What's nice about that is, well, now I can do sine law. Right? I have things that are across from each other. The sine 45, or the 45 degrees, is across from the 800. If I match up the other sides, I've got sine 130 across from R, and I've got the sine of 5 across from W. I'm going to pick two of them at a time and solve them. So I'm going to solve these two. We're going to cross multiply. R sine 45 equals 800 sine 130. I want to get R by itself, so we'll divide out that sine 45. Sine 45. They cancel. I got R as 866.668 kilometers an hour. I could do the exact same thing for the wind one, use the W. And I could use either of the other two because I know what R is now. I'm just going to use this one because it's a nice number, no decimals. And I'm going to cross multiply this way. So W sine 45 equals, and then we'll do this one, 800 sine 5. Divide out the sine 45 again, just like we did the previous one. Same question, right? Just with slightly different numbers in there. And I got 98.6 kilometers an hour. Okay, so hopefully you tried one or two of those yourself to see if you could do it. If not, do we do them together? I've got one more problem for you. We call this the river problem. Okay, it's kind of our typical vectors thing that's not a plane or something like that. All right, so let's take a read here. A person can swim at 3 meters per second in still water. A river is 150 meters wide, and the current is 1 meter per second. The swimmer heads out from one bank perpendicular to the current. So let's draw that. We got ourselves a river. Here's my river. We know it is 150 meters wide. So straight across is 150 meters. We know they can swim 3 meters and the current is 1 meters. So the trick with this is we actually have to think of this as two separate problems. We've got a distance problem, something about the river itself, how wide it is. We've also got a speed problem. So I'm going to draw the same river, and then this time I'm going to talk about speed. Okay. The person can swim, vector, at 3 meters per second. Current is going to push them downstream, so it's going to go down at 1 meter per second. So we've kind of got like a scalar problem, distance, and then we could probably have a speed problem, which is like our vector situation here. Okay. Technically, these two pictures, if you go back to grade 10 math for a second here, are actually the same shape, just different sizes. You might recall that as similar triangles. So we can talk about ratios between these two things. Part A says how far downstream will the swimmer land on the other bank? Well, that's this distance that they're going to end up because the current has pushed them down there. I can solve that by just doing 150 over 3. So we're going to match sides equals distance over 1 because those are matching sides. If we cross multiply this, 3d is 150, divide by 3, and they're going to end up 50 meters downstream. Part B, how long will it take for the swimmer to cross the river? Well, time. How do I find time? Right, time is always equal to my distance divided by my speed. That's always true. How far do you have to go and how fast are you going? Well, you can figure out how long it's going to take you. But technically, we don't have those things right now. We don't know the distance they end up swimming. That would be this. If we don't know how fast they're actually going across the river, that would be this. But we can find those. Those are Pythagoras questions. So for the first one here, we got 150 squared plus 50, that's how big D was, is x squared. Well, x is just the square root of those two things. So x will be, I got 158.11 meters. If we do the same thing for the y one, which is actually the resultant, we got 3 squared plus 1 squared is y squared, or in other words, square root of 10. I got y is 3.16 meters per second. So I have to go a distance of 158.11 meters. I'm swimming at 3.16 meters per second. If I divide that out, shockingly enough, I get 50 seconds. Why did I say shockingly enough? Well, what's the whole point of these two diagrams? Isn't there a ratio? One diagram is 50 times the size of their diagram. Isn't the ratio between these two things right here 50? Like that hopefully would make sense, just like the ratio between these 50 and these two were 50. Okay, there's just the whole idea of similar triangles here. Okay, important question, part C for us. What is the resultant velocity of the swimmer? Well, we already know part of that. We know how fast they're swimming. That was y, right? That was our 3.16 meters per second. The only part we were already missing was what direction are they headed? So to figure that out, we need to know the angle inside the triangle right there, theta. That's a tan question. Tan theta is opposite over adjacent, or in other words, the inverse of that. Okay, calculator. I need calculator, and I got 18.4. All right, here's something we kind of weird about these river questions. Okay, that angle we just figured out is one inside the diagram, which is kind of a hard thing to say. Hey, swim at 18.4. So we don't usually do that. What we do instead is we say to ourselves, and here's the bank of the river. What angle are we making with the bank? Well, to figure that out, we got to think about this as being a right angle up here. So this angle will be 90 minus 18.4, or in other words, 71.6. And the resultant velocity this is something we do generally with all river questions, is 3.16 meters per second at an angle of 71.6 degrees to the bank. Last part, part D. If the swimmer wishes to land at a point directly opposite to the present position, what direction should they head? So for D, thinking about a river, we want to end up straight across, so we should aim upstream, so the current pushes us back downstream. Where should we aim? Well, that's not hard to figure out. If we knew this angle is 71.6 going down the stream, shouldn't we make it 71.6 headed up the stream? That way it pushes us back to where we want to be. Aim at a point, well actually no, not a point, aim upstream at an angle of 71.8 degrees to the bank. Okay, it's the same issue, same problem, same thing we have here, same triangle. That's 3, that's 1. And we just got to aim upstream this time. So we get pushed back to where we want to be. Okay, that's velocity. A couple to try there. If we need to finish some stuff from forces, we can do that too. If we're stuck, we're going to come see me, we're going to talk to me, we're going to figure some stuff out together.